All right, we're going to show you how to do the experiment with the stochastic resonance. Um, this assumes you've already loaded the Scopy SR INI file. Your directory will be different. And you've loaded in the noise new file. Again, your directory will be different. And you can start off at 400 millivolts, keeping everything at 50 kilosamples per second. I used an offset of 2.6. Again, your offset might be different. All right, so I run, I go to the oscilloscope, and there's no transitions. Or I just saw one, but we can see if there's even, really expand this out. And yeah, there's a transition very infrequently, but I found that for this case 5 milliseconds is really the way to go. So this isn't really a good place to start for our experiment, but I wanted to show you what it looked like when nothing was going on. So we'll go back to the signal generator and just type in 500 millivolts, and now we can see some transitions. All right, and we click here so that we can export, and we want to export this as a signal to noise ratio CSV because in our PSOC code we actually have the amplitude set to a non-zero value, so it's actually we're inputting a signal to be detected. Once that's done, you go to your signal to ratio or SR Scopy SR file, making sure you change these directories to whatever is on your computer, right? And if that's the case, all you have to do is run it, and you get the time domain, and you get the power spectrum of the signal. And you can see that near a kilohertz, I've been measuring 1025 hertz consistently. I'm getting a signal to noise ratio of 3.11 for a noise RMS of 0.06. All right, so you can, that's just make sure that it makes sense, and we can use those plots later. But the important thing is there's our theta, and then you would go and let me find it. Under your value, you'd put in 400, you'd put in the theta, then you'd come back and then do the signal to noise ratio. All right, and that would be one measurement. All right, so if you go back to mine, I had done one at 1, I'd done one at 0.5, so I ran it 3 times. And what I mean by that is you export it to signal to noise ratio, replace it, run the analysis, okay, and I get a signal to noise ratio of 3.36 and a theta of that. And you can see that's a, you know, before we got 3.1. It does bounce around a bit, especially at low values of V peak to peak of the noise, right? So then I would do it one more time, save it, yes, and then run the analysis. All right, and I would make sure to put that back in here, and then I'm calculating the average of that and the standard deviation. And 3 seems to be a reasonable amount to take. But when I did 0.5, I actually got a standard deviation of 1.28. And the average was actually less than when it was at 1. All right. So it doesn't give you the same value each time you run it. All right, but let's go try for 0.6. All right, so I come back to the signal generator, I put in 600 millivolts, right? Come back to the oscilloscope. You can see it's transitioning more as we get closer to the 1 kilohertz. Okay. Run the analysis. Okay. And we got a theta here. And I got a signal to noise ratio of 2.29. All right. Then I export it again. I analyze it again. The RMS of the noise is fairly tight. Now, if you kind of get distracted and you get the same exact values as you did the last time, that means you forgot to save the file or something. Okay, it will never be exactly the same. Okay, and then all I have to do is highlight these and drag it. All right, and so you can see, you know, the signal to noise ratio is about 3.03, but the standard deviation was 0.04. That was for 1. Right, this is 3.09. Standard deviation's a bit higher. So it's, these values are kind of meshing into each other, let's just say. There's not much difference. But we should be able to do a plot, let's see, of the average theta versus the average signal to noise ratio chart. Column. I haven't used Google Docs in a while. X-axis. So this is my theta, and you can see that the signal to noise ratio might look like it's going down. When you do this over the whole range, you will see it for low values of noise, lower, then it'll reach a peak, and then it'll go down. But there will be these jumps. To get a more accurate value, it would be great to do 10 measurements per, but that won't be necessary. And so basically, you would do that all the way up to 3.5, right? And you would get maybe similar results to me. Then there's another thing, just measuring the full width half maximum. We kind of do that in the same way. And then once you get those two things close to what I have, right, then you can change the, right, one of you will repeat all that, but for high power bandwidth, low compensation, low power bandwidth, high compensation. So this should be the slowest, and this should be the fastest. So you would do that, build, reconfigure, and all that. But your frequency won't change. Everything will be the same. Your experiment, you'll just change that one. This is just the voltage ref, so we don't have to change that. But yeah, you would just fill all those things out. And then you know, for the poster, you could take one of these plots and like label that that's the peak. You're taking this ratio to that ratio for the signal to noise thing. All right. Now, yeah, as a bonus, we need to measure full width half maximum, but that means we have to turn off the sine wave, which now we're getting into the next part. And we turn that off by, I find it just easier, amplitude equals V peak to peak divided by 2. Let's just multiply it by 0. Okay. And give it a moment. I come back to Scopy, and you can see that it's not really transitioning anymore because the sine wave is missing. So the full width half maximum measurement is taken without the sine wave. And it's non-linear. When you put the sine wave in the noise, you get more out of it than either one by itself. So you can try 800, and now it's transitioning. All right. I forget if 700 works. Okay, 700 works. Now the difference here is you export it, but you don't save it to SNR CSV, you save it to full width half maximum. Okay. And you don't run SR Scopy SR, you run SR Scopy full width half maximum, making sure that these paths are correct, and you would run it. And this time there's no peak, and it's just this curve fit. And the important thing you need is the theta value in RMS and the full width half maximum. And that's for the plot where you do 1 over theta and full width half maximum. But that's actually the next part of the tutorial, but that's really where we're heading. So if we do those two things, full width half maximum for theta and signal to noise ratio for theta at 2 different op-amp configurations, that's our experiment, which would be great. And I'm just going to turn the video off somehow.